Welcome. In this lecture, which has several sessions, we'll explore convexity and level sets. This lecture is where we begin our transition from unconstrained optimization, which is what we've explored previously, into constrained optimization, where we have some additional requirements that a minimizer must satisfy. The main concepts for this lecture are convexity will begin with what is a convex function, and we'll concentrate on affine and quadratic functions, which are like the one forms and quadratic forms that we were exploring earlier in this course. We'll then take a quick look at what positive scaling and addition of convex functions looks like. We'll observe that a convex function is always above its tangent plane, so this is the gradient inequality from scalar land extended into vector land. We'll look at a level set. Previously we had level curves, and now we'll have level sets. And what we'll observe is that a convex set is one that always contains its linear interpolant. An important conclusion, which is a theorem that we won't have time to prove, is that the level set of a function is always a convex set. We can think, along in this lecture, of a problem which is, when is a locally increasing function also a convex function? Let's take a look in the scalar case. So our scalar condition for convexity was that if we linearly interpolate between two scalar values, that is always less than the same interpolation applied to the levels of the function. For a minimizer, what that meant was a monotonically increasing function is simply one where a small change in the function means it has a level that's greater than that at the minimizer. Monotonically increasing and convex are not the same. They're closely related, and it's easy to confuse them, so let's go through a quick example so that we can sort that out. Here's a simple locally increasing non-convex function, and what I did was I took a Gaussian curve or a bell curve and simply flipped it upside down. So what that gives me is from here, which is a local minimizer, and it turns out it's the global minimizer, no matter where we go, we're always increasing. So away from this minimizer in either the negative or in the positive direction, this function is monotonically increasing. It's not a convex function though, because if I take this point and attach them by this chord, the chord intersects the function. And that chord is supposed to be always above the function if it's convex. So this is a simple graphical demonstration that a monotonically increasing function is not necessarily a convex function.